Okay, so let me just turn off my video. All right, so what we have last time we talked about what a continuous function is. Let me get you to the, what does it mean to be continuous? Continuous means the limit at a point, say point A is the same as the function of f at A. So if the value of a function at A is the what I call behavior at a function, and limit when x going to A is behavior near A, around A. Okay, so what you have in this continuous situation is that the behavior of functions around A and at A, they match of these situations. Okay, so what we assume is that of course f must be defined at that point. So to say f behaves in some way at A, and then you have the limit also exists. So behavior of f around A, you can predict the behavior, and then 1 and 2 match up. Okay, so that's what we call continuous. So in picture, so this is what it looks like, or some illustrations. See, around 1, the behavior of the functions, this behaves going to 1. But now the value of the function at 1 is 3. So they don't match up. So this is not continuous. All right. In this case, you see that the value of a function at 1 is somewhere here. The behavior around 1, well, you cannot predict the behavior around 1 because from the right, it tells you that you're closer to 1, but from the left, you're closer to 3. So the limit does not exist. So you cannot tell anything about the, so it is not continuous at 1. Okay. Right. So what are continuous functions? You have polynomials, but this is the case when something what you call earlier easy case, when you compute limit and you just plug in a number, then you get a value, then that's the limit. That's the easy case. That is continuous. Rational function, except at the as long as A in the domain is continuous. So this is reciprocal, also continuous, except at A. Now, sorry, except at 0. Okay, so those are continuous. Okay, composition. All right, so let's continue with this one with more examples. Okay, let's pick up some examples of from the textbook, for example. All right. So let me just show you the screen. Okay. Have you seen the textbook that I'm sharing?
Yes, sir.
All right, good. Okay, let's do some examples. Step 1. Okay. All right. This problem 16 sample. So you have a functions, a piecewise defined functions. So when to the left of 1, it's defined as x plus 1, so linear. To the between 1 and 2, there's ax plus b. A and b is not undetermined yet. And to the right of 2 is 3x. Okay. Okay, so we have to determine the value of this a and b so that the function is continuous everywhere. Okay. So okay, you see the functions. The first one to the left of 1. Well, we'll write down something there, but let me just tell the story about these functions. Okay, so to the left of 1, you see that this is x plus 1, so this is linear, it is polynomial, so it is continuous, right? So between 1 and 2, again, this is a polynomial. For any a, any b, this is polynomial, again, this is continuous. And to the right of 2, 3x, again, is polynomial. All right. So between those three components, you have a polynomial. Again, these are continuous. So the only problem is at 1 and 2. Okay. So those are the things that we need to find out and determine B. Okay, so we want the limit from left, limit from the right at 1 should match up also at x equals 2. Okay. All right, so let's do the problem. Okay, so that's problem 16. Let me I don't know which page is that. Later. Okay. F.
Sorry, sir.
Yes.
One of my friend hasn't been accepted to the Zoom meeting.
Let's see where the. I don't see the. Oh. Okay. Is anyone in the so far I haven't seen anyone in in the waiting room.
Is there by the name Joshua, sir?
Right? All right. Okay, so already in.
Okay, thank you, sir.
What is that? All right, so let's see. X plus 1. to the left of 1, ax plus b between 1 and 2. To the right of 2, it is, sorry, three x. Okay. Now what we say is that on, okay, and between 1 and 2, and 2 f is polynomial piecewise, therefore continuous. Okay, so it remains to check at x equals 1, x equals 2. Okay. Oh, let me move my Wi-Fi because it's getting unstable. Sorry. Sorry, I was disconnected for a bit and then connected, but then it's muted. Okay, can you see my screen now?
Yes, sir.
All right, good. Okay, so let's see. On this part, in these three parts, f is polynomial, therefore continuous. Okay, so remains to be checked at 1 and 2. So let's see. For x, so let's see x from 1 from the left. Okay. So here what you have is these situations. Here you have x plus 1. You have ax plus b. You have 3x. All right. So from the left of to the left of 1, you're going to use this function x plus 1. Okay. Okay, so this has limit. Okay. And to the right, and we're going to use this ax plus b. But it's a linear, that's an easy case when you just plug in number. All right, so just a plus b. Okay. And then that's 1. So from here, what you conclude is that 2 must equals to a plus b. Okay. So also that so there's limit situations. All right, so say at 2 from the left to the left of 2, you gotta use this ax plus b. So it becomes limit. Okay, so just this is the easy case. We don't need this one-sided here. You need one-sided here, but just a regular limit here. Okay, so this is 2a plus b. Okay, and the right limit. Okay, to the right of 2, you see that using this function 3x. Equals 6. And then from the continuity conditions, compatibility conditions, you gotta have 2a plus b equals 6. So you see you have two linear equations with two variables, a and b. So you should be able to determine a and b from these two. Okay. From a plus b equals 2 and 2a plus b equals 6. You solve it. How to solve it? All right, for example, you can subtract them. Okay, you should subtract, then the b disappear, right? So you have only minus a. So this 2 minus 6 is minus 4. Okay. So this a equals 4 and b should be what here? So minus 2. Okay, so that what should be the value for f1 or f2. So that's a and b. Therefore, a and b make f continuous or any real number, x a should be 4, it is 2. Okay. Okay, is that clear enough? So what the geometrically? So geometrically, what you have is this kind of situations. So this is 1, this is 2. So to the left of 1, it's x plus 1. So this is 1, say like this. Okay, and between 1 and 2, it is ax plus b. This is something that we cannot draw yet. Okay, but this is it is 3x. So when you plug in 2, this is 6. Just somewhat quickly. So somehow you gotta draw a line, a segment of line here. To connect. All right. So the question is, what's the equation for that line? Okay, so must be ax must be. So you find the a and b. So it is connected. Okay, so this is what it means geometrically. Okay, questions? No? All right, so again, let's do one more example in this one. All right, so let's go back to this one here, number 40. Oh, section 16, okay, 89. Okay, so define function like this. So this is a piecewise defined also. When x is rational, you define it as x, right? And when x is irrational, define it as minus x. Okay. So you see you have this one here, like this. How you picture this one? So the question is sketch the graph and decide where it is continuous. Okay, so what's interesting in this one is exercise 1.6. Okay, so given a functions x rational and minus x if x is irrational. Okay, so how the graph looks like? Where so we find where is okay. All right, so if you try to draw the diagram, so it looks like this one. Okay, so you can see this is x. X is looks like a this is negative x. Okay, and the thing here is that this is a porous line actually, because you will see under microscope you will see a lot of holes in here. When there is holes here, it should be here. The value should be here in minus x. The same thing here. If this is rational, then the value should be here. If not, then this line. Okay, so both are porous line. Okay, but you can see this is like the amplitude. So whether you click here, okay. So you see that the value of this function is because, for example, here, this is irrational. You can see you can approach this from the left or right using rational or irrational, right? So this is has no limit for any x here, any x here. Okay. But here, the case is at 0. Okay, for x0. Let's do this for x equals 0. Okay. So let's do some squeezing thing. All right. So the value of f is surely say this is between absolute value of x, okay, and this is negative absolute value of x, okay, because the value is just x minus x, x minus x, so this should be bounded above and below by absolute value of x. That happens when for x real number. Uh, okay, so let's see here. You see that this limit that's same as this limit. That's 0. Okay, so this tells you that by squeeze principle, of theorem, you see that's limit. Okay, the same as 0 because 0 is rational. Okay, and for any other x not 0, f is not continuous. Okay, so 0 is the only point where you have continuity of these functions. F is continuous only at x equal to 0. Okay. Questions? Okay, so that's the okay, so let's see. The last thing about this continuity is what we call this is intermediate value theorem. Okay, so what is this intermediate value theorem? So let's read this together here. You have a functions defined on the closed interval. Now it is closed. W any numbers between f of a and f of b. So you see the y-axis between fa, fb. W is a number there. F continuous. Then at this one c between a and b such that. Right. So what this means? This is the picture. So this is the graph of functions f of x, and you have fa is here. Pick any value between f of a and f of b. For example, this is w1. And it turns out there is a c here, which has the value is exactly okay. It doesn't tell you how many c's are there going to be. Right? For example, if you take 2 or w2, for example, here, right? So you see you have C1 has value W2, C2 also has value W2, and C3 is also, so you have 3 points here. Okay, so the fact of the matter is that at least one, there must be at least. Okay, so this doesn't happen if F is not continuous. Okay, so this is the example. This is between A and B. So you see that this is a, it's not continuous at, say, say this is a number, say R. Okay. All right. So if you take W here, you still get something here. Same thing if you take W here, you still have something. This is C. But however, if you take W like this here, you hit nothing here. So there is no C. Okay, so what it tells you geometrically is that any if you take any line between f of a, f of b like this, you always intersect the graph. Okay, so that's what intermediate value theorem tells you. Was intermediate, so intermediate, this is values between f of a, f of b. Okay, so you have some values there. Okay. Let's get value. So let f be continuous. The conclusion is that for any value w between f of a and f of b, there is at least one value c af such that f of c equals w. Okay. So this is a, this is b, this is f of a, this is f of b. Take any value here, just take a line. That's the intersections. A fixed line here, there's intersection. Okay. So this is any vertical line W between f of A and f of B, for example. It must intersect the graph. All right. Okay, let's see how we use this one. How we use this one is by this example, for example. Okay. Okay, I'll explain this one. Let's see. Use intermediate value to show that equation x minus cosine x has a root, has a solutions between x0 and x pi over 2. Okay. All right. Okay, change that. I'll give you another example instead. You can read this one from the textbook maybe. Let's find something different from the exercise. All right. Okay, here, 52. Use an intermediate value to prove that there is a real solution between 0 and 1. Okay. And I would add something else here. Let's see. Let's see, x cubed minus plus 3x minus 2. Which is 0. Let's do this one. Sorry, which problems at 52. Okay. IVT, I call it IVT, intermediate value theorem. Show using IVT that x has a root between 0 and 1. And then I would say something further. Approximate with error, say, less than 1/8. Okay, let's see how to do this one. All right, so let's think about the, say, to use IVT, you gotta have the functions, but we don't have function here. Okay, so let's define, this is the functions. So this polynomial. So this is polynomial. For every real number. Okay, so that's the problem. We can use IVT. Okay. All right, and let's observe also that if you plug in 0, you have, let's see, plug in 0, then you have -2. Okay, and if you plugged in 1, you have, let's see, 1, 1. Okay, so you have 2 positive. Okay, so pictorially, it looks like this one. Oh, sorry, so 1. Of course, you don't know what the graph looks like, except if you plot it using apps or whatever. Okay, but the value is -2 here. Here you get a 1. So your task is, because this continuous, then you should be able to connect these 2 points, whatever, by continuity. Should be able to connect these 2 points. But when you connect these 2 points, you cannot avoid intersecting x-axis. X-axis. That's the intersections. Okay, so that's basically what the IVT tells you. If you take this one, see, this is how. So F1 is negative, and F2 is positive. Okay, sorry, this is 0, this is 1. And f is continuous on 0, 1. Then by FET, there is C at least 1. So that FC equals 0. And where the C is between 0 and 1. So this show you the root of f. Okay. All right. So what's the approximate value of C? First approximations. First approximations. Well, we can say C is between 0 and 1. So it's fair to say that C1, I would say, is, I write this like this one. Say 1/2, right? But plus minus 1/2. Okay, so it's fair to say this one. So the root is 1/2 with the error of 1/2. This is just to say that C1 is okay. See what I meant here? Questions?
Excuse me, sir.
Uh-huh.
Sir, I would like to, can you repeat again, like how you get the approximate value for C? How you get the half plus minus half again?
All right. Because we know from here C exists, right? There is such a C, but we don't know what the value of C, exact value. Okay. So just to say that C is between here. To say that C is between, so C is inside 0, 1 is the same as saying that C is 1/2 plus minus 1/2. Right? So just pick the C somewhere here. So where's C? To make it symmetric, just picking something in the middle. Right? So say this is the error. Okay. So this
Okay,
is just to say C between 0 and 1. This happens if C 1/2 plus minus 1/2. So know this one. But the thing here, we asked that the error should be less than 1/8. So how to do this one? Okay, so let's do this one. So let's repeat this. Right. So let's check this one. So compute f of C1. So let me write this down. Okay, so this 1/2 cube plus 3 times 1/2 minus 2. So what you get here? So this 1/8 plus 3/2. 2. Okay, what's the value? We don't need the exact value, but we should be able to decide whether it is positive or negative. So this is 3/2 minus 2, still minus 1/2. Minus 1/2 is larger than, sorry, 1/2 is larger than 1/8. So this should be negative. Okay. No need for exact value. Only its sign. Yes. Positive, negative. Why? Because, all right, so this is the everything. 0, 1. Okay. So at 0, this is the values between. 1 is somewhere here. Okay. So there must be intersection between 0 and 1. Okay, so that's C1 is. All right, now at C1, 1/2, you see, the value should be negative, so below the x-axis. So where's the intersection should be? Between 0 and 1/2 or between 1/2 and 1? What can you say? Where's the intersection located? Between 0 and 1/2 or 1/2, 1 for sure. You see what I mean?
Yes, sir.
So between 0 and 1, because this is negative, this is positive, the graph is continuous. There should be, somehow it should cross the x-axis. Okay, somewhere. We don't know yet. Okay, now between 1/2 here, at 1/2, this is below the x-axis. Okay, so the thing here, what if I connect this to this? Will you intersect the x-axis? You may not. Okay, if you connect, you may connect like this, and in this case, there is no intersection. But if you have this, you may have intersections. The thing is, you cannot be sure whether connecting these two give you a root. Okay, but if you connect this 1/2 with this one, sorry, do you see my you should be able to, okay, okay, you see pointers. No, the thing is, it should be able my pointers. All right, okay, so forget. If you have to connect these two points, all right, you cannot avoid crossing this x-axis. Okay, this is what I'm saying. Connecting this f1/2 to f1, you cannot avoid intersecting x-axis. What this intersection means? Intersection, that's the root. This is IVT tells you. So by IVT, there is root C2, right? inside. Okay. So what's the error? Right. In this case, C2 is, say, pick the middle point of 1/2 and 1. So that's 3/4. Okay. So what's the error? What is the error? So if you pick C2 here, what's the error? What's the error again? Why 1/2? In this picture here, what is the error? What distance?
Is it 1/4?
Yes, because this going to here, that's the error, and here to the left. To the right, this is 1/4. To the left, 1/4. So this is 1/4. Okay, so this tells you that C2 is actually anything between, say, 3/4 minus 1/4. This is 1/2, and 3/4 plus 1/4. That's 1. Right? So this expression sorry. This expression and this expressions, okay, is actually same thing. Okay, so this is error 1/4, right? So this not good enough, because what we look for is error, let's see, sorry, going 1/8. So let's do this one more time. So now we say this is our first step, first approximations. Okay. This is our second approximations. Okay. And let's see. Third approximations. Okay. So let's see. Now it's between 3/4 and so this is the situations. This is 3/4. Okay, so let's check this value. Okay, so let's compute this one. So 3/4 cube, but plus 3. Okay, so what we have here, so cube, 4 cube, 16, 64. Okay, so this gives you 3 cube, 27. Here you have 16, 32. 32 times 3, 96. Correct? And sorry, this is should be minus 2. Okay, minus 2 minus 1. 28. All right, so let's see. The question is not computing this exactly, but the sign on the positive, negative. So what's this looks like? 128, this is 96. So you have 130. Sorry. No, you still have negative, right? Okay, because 27 plus 96, that's 123. Okay, so that's negative. Okay, so here's our situations. Here's negative. Here's negative. Here's positive. So guess what? Where's the root located? Here or here? Where C3 located?
Excuse me, sir.
Mm-hmm.
Sorry to interrupt you, sir, but I checked in my calculator. The f of 3, 4 is positive, sir. It's equal to
Positive?
13 over 16.
13 over 16. Let's see. Uh,
It's 3 over 4 square plus 3 multiplied by 3 over 4.
by square. By square. You don't have square. It's cube.
Oh, wait.
Because if it's square, then we have, you know, that the quadratic equations, we can find out the exactly. We have formulas for square. That's why the problem is the cube. Okay.
Okay, sir.
Okay. So just guessing these two. Where's the CT must be located? Between 1/2 and 3/4, or between 3/4 and 1?
Is it between 3/4 and 1?
So it must be here. Must be different sign. If different sign, then you have to cross x-axis to connect them. Okay. If you have the same sign, it doesn't, well, it may cross the x-axis, but you cannot be sure about that. So by SE3, there exists C3 between that f of C3 is 0. Okay. All right, so let's say here, just take the, again, the C3 is, let's see, what is this? C3 is between this is 6/8. So this is 7/8. Right? What's the error?
One-eighth.
1/8. There we go. That's the error that you require in the beginning. Okay. So then an approximation to the error is 7/8 with error 1/8. Okay, so you get the approximations. Okay, now check these functions. Use your calculator, compute this. Check this. So you compute this. What you get?
The result will be positive, sir.
What?
It will be positive 89 over 64.
So now we need the value, not the sign here. What's the value here?
89 point, no, sorry, 89 over 64.
59.
89 per 64.
Is that true? Cannot be 64. You sure this is number?
Wait, let me check, sir. Oh wait, is it cube, sir?
Cube.
Oh, then it will be 663 over 512.
Not sure though. Should be smaller than that.
Maybe someone can check in
Uh-huh.
his
Someone can
portal.
check the computations.
The answer is the same, sir. But
Same. Hmm.
Yeah, I also got the same one, sir.
What's the number in decimal?
Oh, in decimal. 1.294. I mean, just 1.3.
1.3. Okay. Let's see. Oh,
Excuse me, sir. It's 1.3. It's 1.3.
1.3. All right, doesn't matter. Just this number, right? 1.3. Okay. Do you have something like? Okay. We'll use the something like, okay. We'll use maple. Let me check using the something. Okay. Do you have you have apps on your mobile phone, something like Wolfram Alpha or something else? Okay, I'll show you. Just use this one. Okay, use Wolfram Alpha. Where's my Wolfram Alpha? Oh, yeah. Okay. So let's see, x cubed plus 3x. So sign 3x minus 2. Right. Hey, something missing here. Let me check. Minus 2. I missed something. Did we? Right. 1/2. 1/2 is Q. Eighth. We have.
Sir, I think the value of f3 over 4 is still wrong. It's positive, but it's not. It's 43 over 64.
This positive?
Yes, the 3/4, 3/4, not the half.
That's positive. 3/4 is positive. Oh, this one is. So you mean this one is? We are wrong in this one.
Yeah. It's
okay.
43 over 64. It's the value, the final value.
All right. All right. Okay. That is incorrect. 16. Yeah. All right. So this one should be positive, right? Oh, okay. So then this tells the. Okay. So then what we were wrong at the time. I was wrong, not you. All right. So this should be positive. Then, all right. Here. Okay. Then the intermediate value theorem says that C3 is not here, but must be between 1/2 and 3/4, right? So this is what we get from 1/2 and 3/4. Okay, so then it's not 7/8, but let's see, between 1/2, between 1/2 and 3/4. 3/4 is let's see, in 8. What should be the middle point? So this is 1/1. So the 1/2, I think this is 8. For 8, it is 6/8, so it's 5/8. Okay, 5/8 plus minus. There we go. Okay, so then what we need to compute here is that let's see how to go this one. Sorry, I want to erase this one. So what we need to compute here is just this one. All right, so f of 5/8. Okay, so it is f of this 5/8. Okay, when I use apps, it gives you the value is, let's say, okay. You can plug in the number 5/8. You find this number here. Or from Alpha Apps. C3 is 1.596 from that point. And 5/8 is, let's see, 5/8 is 5 divided by 8. Okay. Set through 5/8. Yes. So this is there. Okay. So you see that this number is between this one, within this error, margin of error. Okay. And how to do this a more get a precise number? Yeah, repeat this the steps, and you can get any precision that you like. It's not efficient, but it works. Okay, questions?
Sir, I want to ask.
Sure.
Earlier you explained with the phrase of roots.
Uh-huh.
What do you mean by roots in this context?
Roots is something that you plug in, gives you 0.
Sorry, sir, can you explain again?
Roots. That's root of f means f of c equals 0. If you're plugged in, then you get 0.
Oh, okay, thank you, sir.
Okay. Other questions? All right. If not, then let's take a break for 5 minutes.